Okay, so on notes 1-4, we're going to be verifying that two functions are inverses of each other. So there are two different ways to determine this. We can determine graphically and algebraically. So in number 1, it says determine if the following graphs are inverses. So remember, whenever we were finding an inverse graph, all we did was we flipped the points. So that's one way of figuring out if they're inverses. Look at your points and see if they're flipped. Also, another way is if they intersect. So if they cross, then it must be on your reflection line, which is y equals x. So if they intersect, they must intersect or cross on your intersection line, which is y equals x. So notice here they do intersect, and it is on that y equals x line. So again, they don't have to intersect, but if they do intersect, it has to be on the y equals x line. So again, remember, you can just look at your points too. So this is -1, 1. So the reflection point should be 1, -1. And notice we have that point. And then you can continue on and look at the other points. So yes, these would be inverses. So graphically, check your points, make sure that they're flipped and reflected across the line y equals x. If they intersect, they have to intersect or cross on that y equals x line. Okay, number 2, we're going to determine if the two functions are inverses graphically. So notice this one, we are not given the graphs. So we're going to have to find the graphs first, and then we're going to determine if they're inverses. So since both of these are linear, we could plug it in the calculator, but we can also use slope and y-intercept. So on this first one, the slope would be 1/3, and y-intercept's 2. So it's going to cross at 2 on your y, and then we're going up 1, right 3. Up 1, right 3. And I want to go ahead and extend it throughout the whole graph, so that way I can make sure those points match up if they're inverses. So there's my first one. Then I want to graph g of x, which is 3x minus 2. So on this one, the slope would be 3/1, and y-intercept's -2. Again, if you have a calculator, you could also plug it in and look at the table. Okay, so this one is crossing at -2 on the y, and then we're going up 3, right 1. So I'm just going to go ahead and plot all the points that are on our line. And then also we need to go ahead and remember, draw our reflection line, which is y equals x. This is very hard to do. I'm going to delete that. And I kind of erase those other points. Okay, so we can either check the points, look and see if they're flipped. Notice they do intersect. They are intersecting at this point here, which notice that is not on our reflection line. So again, you can either check the points, or if they do intersect, it has to be on that y equals x line. So notice here we could check a point. This point here is 0, 2. And notice we do not have a 2, 0 point on the other side. So we know these would not be inverses. If you want to write down y, because points aren't flipped, and also they don't intersect on your reflection line, which is y equals x. Okay, so that's how graphically we can determine if two functions are inverses of each other. Let's look at the back. Oops. Okay, so it says if functions f and g are inverses of each other, then f of g of x, which is composite function, equals x, and g of f of x equals x. So algebraically, what we're going to do is we're going to plug in using composite functions and make sure both of those equals x. So f of x is going to be 2x plus 4 on this first one, and then g of x is 1/2 x minus 2. So I'm going to start out with doing f of g of x. So remember, the inside is your input. So I'm going to go ahead and rewrite that as f, and I know my g is 1/2 x minus 2. So I'm replacing that in function f. So I'm inputting 1/2 x minus 2 for x into function f. So I should have 2, then parentheses 1/2 x minus 2. And then notice on this, after we plug in for x, we have a plus 4. All right, so I'm going to need to distribute. So 2 times a half x is just an x. 2 times a negative 2 is a negative 4, and then we're bringing down that plus 4. So notice negative 4 plus 4 is going to cancel. We're left with x. Now, just because one works doesn't mean the other one works, so we have to plug in both. So now I'm going to do g of f of x. All right, so I know f of x is my input, and f of x equals, hang on, f of x is 2x plus 4. So that's what I'm going to be inputting into function f. Okay. All right, so I have 2x plus 4, and looking in front, I have a g. So in place of x on function g, I'm going to replace it with, my colors are mixed up. So 1/2, place of x, I'm putting 2x plus 4. And then notice on function g, after you plug in for x, you also have a minus 2 there. So I'm going to go ahead and distribute. So a half times 2x is just an x, 1x. Half times 4, so half of 4 is 2. And then I need to bring down that minus 2. So notice 2 minus 2 cancels out, so we're just left with x. So notice at the beginning, remember we talked about, or at the top, we talked about they both have to equal x. So since they both equal x, then we know these would be inverses of each other. So that's one way algebraically to determine if your two functions are inverses. All right, so example 4, we're going to determine both algebraically and graphically whether or not f and g are inverse functions. All right, I'm going to go ahead and start with algebraically. So I know I need to do f of g of x so I know my input is my inside, which is g, function g. So I have 1/4 x minus 3. So I'm inputting 1/4 x minus 3 in for x on function f. So I have 4 in place of x. I'm putting 1/4 x minus 3. And then I have a plus 3. I'm going to distribute. Make sure you distribute. 4 times 1/4 x is just 1x. 4 times a negative 3 is a negative 12 plus 3, which does not equal just x. Now, you could stop here, because if the first one doesn't equal x, then we know that they're not inverses. Now, you could have made a mistake, so you might just double check the other. So if we do g of f of x, my input is function f, which is 4x plus 3. So I have 1/4 replacing x with 4x plus 3, and then minus 3. So when we distribute, we get x. That's going to give me 3/4 minus 3, which does not equal x there. So we know algebraically it doesn't work, which means graphically it shouldn't work either, but let's just double check. So we need to, it tells us to do both. So I'm going to graph, since both of these are linear, I'm just going to use slope and y-intercept, but it doesn't really matter. If you want to use the calculator, you can plug it in and look at your table. So my y-intercept on function f is 3. And I'm going up 4, right 1, down 4, left 1. And then function g, y-intercept's negative 3. I'm going up 1, right 4. And then I'm going to go ahead and draw my y equals x line. Okay, so you can either check the points, and then, but notice that they do intersect. So if they do intersect, they don't have to intersect, but if they do, it has to be on your reflection line. So notice they do not intersect on that reflection line. So no, these are not inverses. So that's how we can show algebraically and graphically that they are not functions. Okay, so number 5. First, algebraically. So I'm going to do f of g of x. So my input is g of x. So g of x equals 1/3 x minus 2. So I'm going to input that into function f. So I have 3. In place of x, I'm putting 1/3 x minus 2. And then plus 6. So I'm going to distribute. So that's just going to be an x. Make sure you distribute the 3 to the 2, so negative 6 plus 6, which those cancel, and it equals x. Have to make sure the other part works. So g of f of x so my input is f of x this time, which is 3x plus 6. I'm going to replace my x on function g with 3x plus 6. So when I distribute, that's going to be just an x. That's going to be 6 over 3, which is 2, minus 2, which equals x. So both of those equal x. Now let's show graphically that these would be inverses. Okay, so again, these are linear, so I'm just going to use slope and y-intercept. 1, 2, 3, 4, 5. So it crosses at 6. And then we're going up 3, right 1. And then down 3, left 1. And then function g, it crosses at negative 2. And I'm going up 1, right 3. And drawing my y equals x line. Now, if you're looking at the intersection point, you need to make sure that it should be dotted. Make sure that your reflection line is pretty accurate, because you're wanting to see if it's intersecting on that line. So notice it does intersect on that line. Also, you can check the points and make sure that they're flipped. So yes, these would be inverses. So that's verifying that two functions are inverses algebraically and then also graphically.